Hello and welcome to a new lecture of classical motion of a single particle. In this lecture, we will discuss the concept of limit cycles. Okay. Till now, we have discussed the dynamics in two-dimensional phase space of autonomous systems, okay, where in the laws of dynamics, there was no direct appearance or explicit appearance of time. And for such a system, we actually found that always the fixed points were discrete points, and we said that somehow if those fixed points are reached or we start by preparing the system in those fixed points, then there will be no evolution at all. But this is actually true for only a linearized system in two-dimensional phase space. In two-dimensional phase space, if we take nonlinearity into account, we can actually create, for the very special case, you can think of a closed orbit type of set of points, which actually is working as an attractor and repeller, and it is not permitting any other closed orbit in the neighborhood of that. So, this is really a discrete one. So, it acts like a discrete set of points, okay, which does not permit other closed orbit type of trajectories in the neighborhood of it, okay, and such type of orbits are known as limit cycles. Okay. But once again, the limit cycles are possible only if we go beyond the linear systems. We have to take nonlinearity into account. Okay. So, before even starting that, I would like to also mention a point that this type of isolated trajectory, isolated closed trajectory is not possible in the case of linearized systems, okay, because in linearized systems you can also have sometimes closed trajectories just for let us say for the case of a simple harmonic oscillator you can have, but then you can always have another closed orbit very close to the original one. Okay. For example, for the elliptic phase space orbits, you know, if you just change the energy just by a very slight amount, okay, if you now manipulate the mass of the particle, you manipulate the stiffness of the spring a little bit, then you can always find an ellipse which is very close to the original ellipse, okay, or the previous ellipse, and that is why it is always possible to create an ellipse which is very close to the first ellipse, okay, and it cannot then be thought to be a discrete or separated ellipse. Okay. But in nonlinear systems, you will see that it is possible to create a totally discrete closed trajectory. Whether this is ellipse or not, I am not telling anything. Now, let us do a very specific example and we can understand how it works. So, you just first take the very example of this 2D phase space dynamics. X dot is equal to mu x plus y plus x times x square plus y square, where mu is a constant. Okay. Y dot is equal to minus x plus mu y plus y times x square plus y square. Okay. Now, first we will check how it behaves for linearized situation. Okay. So, when linearized, we have x dot is equal to mu x plus y and y dot is equal to minus x plus mu y. The other terms can be neglected because of the very small values of x and y, okay, because it is a linearized system. Then what is the coefficient matrix A? The coefficient matrix is mu 1 minus 1 mu. Okay. So, if you have such a matrix, then you can actually easily say that if lambda, now if lambda is the eigen value of A, then mu minus lambda 1 minus 1 mu minus lambda would have 0 determinant, and you can say mu minus lambda whole square plus 1 is equal to 0, okay, which actually gives you mu minus lambda is equal to plus minus I. Okay. So, lambda will be actually equal to mu minus plus I. Okay. Now, you see, you can easily conclude about the phase space trajectory from our previous discussion. So, if mu is less than 0, then so this is a case where your eigenvalues are complex, okay, and the mu can be positive or negative or 0. So, if mu is less than 0, of course, you will have an asymptotically stable spiral point. If your mu is equal to 0, then you will have simply orbit, okay. And if your mu is greater than 0, then you will have, okay, unstable orbit, means that then your lambda will be simply minus plus I, okay, just like an oscillation. Unstable spiral point, okay. But these three type of fixed points are obtained for different values of mu. That means, you are actually changing the parameters of the system, so that they are corresponding to three different systems. Okay. That is the best what we can obtain for a linear system. Now, for non-linear system, we can obtain something which is much more interesting. So, for non-linear system, if we take the nonlinearity into account, then, okay, it is better to convert everything to plane polar coordinate system. This is not hard and fast, this is just from the specific form of these two equations, okay. And we will actually see that how it helps. So, in plane polar coordinate system, once again, in 2D plane polar coordinate system, I can write r square is equal to x square plus y square, okay, and theta is equal to tan inverse y over x, okay. And then from this one I can write directly, from this one I can write that r dot, so there will be a 2 which will be cancelled throughout, okay, x dot plus y dot. You are just taking the ddt on both sides, okay. And from this one you can get theta dot, that will be equal to, first of all, 1 over 1 plus y by x whole square, and then ddt of y by x, which will be x y dot minus y x dot by x square. Yeah. Okay. So, finally, it will be x y dot minus y x dot by x square plus y square. Okay. So, finally, what we obtain is this r dot is equal to x, and instead of x dot I will now write their values. So, x dot, if you remember, it is mu x plus y plus x square plus y square plus y dot, which is now minus x plus mu y, okay, plus y x square plus y square. Okay. And if you now do this calculation, you will see that mu times you will have x square plus y square. X y and minus x y will go away, plus then you will have x square plus y square times x square plus y square. So, you will actually have x square plus y square times mu plus x square plus y square, and this is nothing but r square mu plus r square. Okay. You can actually check this thing, and now since you have also in this side 1 r, so I can cancel 1 r from both sides, and I can say r dot is simply equal to r times mu plus r square. This is my first equation in polar coordinates. Okay. I can also go for the second one. So, I can write again for theta dot, I know that r square theta dot. So, if you remember, this is r square. So, r square theta dot is x y dot. So, x time, which is y dot is minus x plus mu y plus y x square plus y square, okay, minus y times x dot, which is mu x plus y plus x square plus y square, okay, and this is equal to minus x square plus y square. So, I am taking this term and this term, then you will have mu x y plus minus, they will go away, okay, and finally, you will have plus x y x square y square, that will also go away. So, finally, you will have just this, yeah, and you see the amount of simplification which we really get is commendable. Theta dot is equal to, so this is nothing but minus r square, theta dot is equal to minus 1. Okay. So, you see that already if we do the polar transformation, okay, we saw that theta dot is negative and constant. So, with time theta is always decreasing at a constant rate. Okay. Now, what happens for r dot? R dot in general, if mu is positive, then everything is positive. So, r is always increasing with time. Okay. It simply gives you a picture of a spiral. Okay. I am going to that in more detail. So, if I am just taking a color, okay, if mu greater than 0, okay, then r dot is positive always because of this expression, this. If mu is greater than 0, then r dot is always positive and theta dot is constant and negative. Okay. So, we will always have spiral for which the theta dot is actually decreasing steadily with time. That means, the theta dot is increasing maybe in the clockwise direction, okay, and r dot is positive. So, r is always increasing. So, we can simply draw the picture like this. So, we can say, okay, the phase space trajectory should actually be obtained like this, okay, where I have a spiral type of thing, and this spiral is actually an unstable spiral because the spiral is going outward, but the angle is always in the increasing in the clockwise direction. That is why it is given by theta dot equal to -1, which is theta dot is less than 0. Okay. So, you can have this type of possibility. Now, what happens if mu is less than 0? Then you see you have r dot which is equal to mu plus r square times r can be written as r square minus alpha times r, where alpha is equal to minus mu and greater than 0. Okay. Then if alpha is constant, of course, if r is changing and r is such that r square minus alpha is greater than 0, that is r greater than root alpha. If r square minus alpha is equal to 0 and if r square minus alpha less than 0. Okay. 3 cases are possible, that means r is equal to root over alpha and r is less than root over alpha. Okay. What will happen in these 3 cases? So, first case, okay. So, you see that this thing is positive. So, r dot is positive. So, r is increasing with time and theta dot is always -1. Okay. So, you will have, I am just drawing the phase space situation. Okay. So, this is exactly r is equal to root over alpha. When r is greater than root over alpha, okay, what happens that r is increasing and theta is actually decreasing. So, it is actually given by something like this. Okay. So, an outward spiral, but in clockwise direction. Okay. Outward spiral in clockwise direction. Okay. Now, if r square is less than alpha, that is r is less than root alpha, that is for example here, okay, then what happens that r dot is decreasing because this is negative and theta dot is also negative. Okay. That means, this is also clockwise spiral, but which is inward moving, okay, like this. Now, what happens at this point, this pink point? Before that, let me just write it down. This is nothing but an inward spiral in clockwise direction also. Okay. Clockwise direction. Okay. In between the two, this one is the case where r is equal to root alpha, and that means at this point what happens, just at this value, what happens, your r dot is equal to 0 and theta dot is equal to -1. So, it is simply a clockwise circle. Okay. But this is true only for one specific value of r. If you just perturb this value Okay. That means, you say now my r is root over alpha plus minus epsilon, where epsilon is even very small tending to 0. Okay. It will either be an outward spiral or be an inward spiral, but no longer the closed trajectory. So, the closed trajectory is actually only possible for a very specific value of r, which is given by root over alpha or root over minus of mu. Okay. Now, you see here, just for a given value of mu, just by varying the value of r, you can achieve 3 type of phase space trajectories, and in between you have a closed loop, and inside and outside you have 2 different type of spirals. So, outside you have an outward spiral, inside you have an inward spiral. Okay. So, what is the nature, if I now think about this specific closed loop, actually if you just go a little bit inside from this one, okay, you will find the spiral is actually going inward. So, the spiral is going away from this loop, and if you are going a little bit outside, you will have an outward spiral which is also moving away from this loop. That means, neither the inside spiral nor the outside spiral actually want to get close to this loop. Okay. So, this is called an unstable limit cycle. Okay. So, I can think of this is just like an attractor or repeller, but here it is actually, to be very precise, it is a repeller, but this is not a point repeller, this is a repeller which is an ensemble or a collection of a continuous, okay, set of points. I can also have another type of limit cycle, which is the stable limit cycle, where the picture should be like this, that something I have like this, okay, and inside I will have a spiral, where the spiral actually would be an outgoing spiral. So, inside spiral will be an outward spiral, okay, maybe clockwise, okay, no problem for that, but if the inside spiral is outgoing or outward, then this limit cycle I can draw with a different color actually. This limit cycle, okay, is in a sense is attracting this spiral, and you will see in that specific case also the outward spiral will be in that case. Since I have drawn clockwise, I can draw a clockwise one always, okay, and I can say that, okay, this one will actually go like this. Yeah. So, you see the, yeah, so, yeah, that is possible. Okay. Here you see that this is coming inward direction, and the inside spiral, okay, this is going outward direction. Okay. And in both cases actually these two trajectories are trying to approach this limit cycle, and that is why this limit cycle is called a stable limit cycle. Okay. Now, what is a very important advantage for limit cycle? You see that this is like a magic in a nonlinear system, whereas you cannot think of any oscillation, because oscillations are more like for linearized system. Okay. A small perturbation with respect to some stable equilibrium, your system is linearized, and then you can think of oscillation. But here you have a situation where you have an oscillation, because whenever you have this type of closed loop, actually what happens that you have an oscillation, okay? And that means that you have an oscillation in a suddenly out of nothing in a nonlinear system, and that is only because the specific adjustment between the phase space coordinates and the parameter, okay? And this type of oscillations are very interesting for both physicists and nonlinear dynamists. One such example is van der Pol oscillator, okay? I recommend you to learn more about this and to understand their advantage, okay? Just the last point before wrapping up this lecture, that is, if in a system you can predict whether the system has a limit cycle or not, many things can be easy, but predicting a limit cycle is not easy. Here you see that you have just done coordinate transformation from Cartesian to polar, and suddenly you find the limit cycle, okay? And sometimes, and from actually from the Cartesian point it was not very evident, okay? You can try. Now the point is, from different systems it may not, from some systems it may not even be evident even in the polar coordinate system, maybe some other coordinate system. So, it is a trial and error process. So, I mean whether a system has a limit point or not cannot be easily said, okay? But sometimes there are some theorems or some features by which we can say that there can be a possibility of limit point, okay? Or there is an impossibility of having a limit point, and the second one is much more popular, because the second one is operationally much more easier. So, if for example, for a very simple case, that if in your system you can show that for that system no closed trajectory is possible, never ever, then of course it automatically eliminates the possibility of a limit cycle, because limit cycle is of course one possibility, I mean one possible closed trajectory, right, in phase space. So, if somehow you can show that your system does not permit in phase space any type of closed trajectory, whatever be the value of the phase space coordinates and the parameters, no closed trajectory is possible, then already you can say that okay, I will not search the possibility of a limit cycle. If you can show that there is a possibility of closed trajectory, then whether that closed trajectory is a limit cycle or not, or some of them can be limit cycle or not, that is of course to check, and this is again there may or may not be any clear cut recipe for that. One example definitely saying that there is no limit cycle possible is the system which we in general say the gradient systems. So, limit cycles, I am just saying that limit cycles okay, are impossible for a system which do not permit, which does not permit a closed trajectory in phase space. Okay. Now, actually if I have a system in 2D phase space always, x dot is equal to and y dot equal to something and something, but this something can be written as a minus delta v delta x, and this is given as minus delta v delta y. Okay. This minus is just for convention, okay, where v is a scalar function of x and y. If it is written like that, then this type of system is known as gradient system, and for gradient system no closed orbit possible, and that is why no limit cycle. Okay. There are other theorems and there are other properties by which one can actually also check whether there is possibility of limit cycle or not, but this is currently the beyond the scope of this course. Okay. Thank you very much.